name recommends selection. What do you select? We select minimums. Remember, as the name recommends, what do you select? We select minimums. So the name recommends select minimums. So what you will do is you look at the entire ad and I will say who is the minimum, and it says 9 minimum. So you click that 9 and you place it here. Perfect. And place the 9 and if this 9 is the minimum and it is at the first place, where will it be? has to come at first, and now I'll write the remaining guys over here. That's how you do it. So that is the step 1 of the algorithm. Step 1 states n times, exactly, yes. Next time when it gets in, then this actually runs for one lesson. It runs for 1 to n minus 1. So when I say it runs for n minus 1, next time when it gets in, it runs for 1 lesson. So it's like n minus 2. Next time when it gets in, it runs for 1 lesson. You need to do for a single element. You do not. Thereby the entire array is sorted, if you see. So so you have understood the algorithm. But now the key factor comes in, which is implementing this to code, because that is where the key lies. Next, 50 to 20. So you have understood the selection sort algorithm in depth. Let's try to analyze the time complexity of this particular algorithm. Let's see. Can I say, for the first time when the loop gets inside, this particular loop runs for n times, exactly, yes. Next time when it gets in, then this actually runs for 1 lesson. It runs for 1 to n minus 1. So can I say it runs for n minus 1? Next time when it gets in, it runs for 1 lesson. So it's like n minus 2. Next time when it gets in, it runs for 1 lesson. N minus 2. So on, it kind of runs for till last. The last that we run for this is till here. That's for 2 times. So this is kind of if I just try to take it to some near formula stuff, can I say it's something like 1 plus 2 plus 3 plus dot till n, which is nothing but the summation of the first n natural numbers, which is n into n plus 1 by 2. Can I say this? I can. So if I can say this, what is this? N squared plus n by 2. Can I say this is how it looks like? And if you remember the time complexity, we ignore smaller things because n by 2 in comparison to n squared is very small, and we ignore constant. Thereby, I can say that the time complexity is near about big O of n squared, and this is the best, this is the worst, and this is the average time complexity for this particular algorithm. So we can say that we have completed selection sort successfully. Let's try to understand bubble sort. Bubble sort. So when you talk about bubble sort, you have to remember it pushes the maximum to the last and opposite to the selection. Because selection sort was taking the minimum at the front, if you remember. Pushes the maximum to the last. How does it do it? By adjacent swapping. Adjacent swapping is the key over here. How does the algorithm work? Let's understand. First 2 elements, compares. Are they in the sorted order? 13 and 46, they are, because 13 is smaller than 46. Do not do anything. Go to the next 2. Are they in the sorted order? 46 before 24. No. Swap it. Okay. Swap. 24. 24. 46. Perfect. Let's go to the next. 46, 52. Are they in the sorted order? Yeah, they are. Why will you do anything? Next. 50 to 20. Are they in the sorted order? No. 20 should be before. Take 20 here. Take 52 here. So 20, 52. Let's go to the next. 50 to 19. Are they in the sorted? No. So take here. Take here. So let's do 9 and then 52. So can I say, after adjacent swaps, like this, like this, like this, like this, like this, one complete round of adjacent swap pickings, do you observe something? The max 52 is at the last. The max 52 is at the last. Done. So the max 52 is at the last. What should be your next step? This portion of the array is kind of sorted. So I need to work on this. But from the same algorithm again, let's do it. 1324, is it okay? It is. 2446, is it okay? It is. 4620, no, 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 no. Swap 46 here, take 20 here. Let's swap it. 20, 46, let's do the next. 46, 9, are they? No, no. Take 9 here, take 46 here. 9. Do you compare the last two? There's no point. Because 52 is already in the solid right. There's no need. You only do it till here. Can I say now? Optimizations. Let's go and do some optimization. Can I say, if I say id did swap equal to 0, and over here if I just can say did swap equal to 1, which means it always takes an element and places it in its correct position. Take insertion. So you need to remember one thing. It always takes an element and places it in its correct position. Takes an element and places it in its correct position. Let's start. Yeah. The algorithm starts with looking at the first element as an array. And you will say that if this much is the array, the element 14 in a size 1 array is at the correct. If I look at this much and ask you, is 9 at the correct position? You'll be like, no. 9 apparently should have been here and 14 should have been here. So this is what you do. You go to the next element and you ask on the left side where 9 should have been. And that is where you take. So you basically do it like this. 9, 14. Perfect. So then you go ahead to this one and you ask, is 15 at the correct position for a size 3? And you say, then you go ahead and say, is 12 at the correct position for a size 4? And you say, no. Apparently 12 should have been here, 14 should have been here, 15 should have been here. So do you see a pattern? It's like 14 will come here and 15 will come. Everyone right shifts by 1 and 12 kind of goes in its correct order. So what you can do is, you can take 12 and you can say, okay, 12, 15. 15 will come here, 12 will go here. Then you can say 12, 14. So you can 12 here and you can pass 14 here. You can go to the left and swap, swap, swap till it can be swapped. Till it can be swapped. So if you do like this, 12 goes here, it's like 12 and 15. Then 12, 14. So 12 goes here and 14 comes. So go to the left till it can be. Can 12 be swapped with 9? No, because that will distort the order. But just go still here. Simple. So what will happen? It will be like 12, 14, 15. Perfect. Next is 6. If you look at 6, where ideally should be 6 in this array? It should be here, 9 should be here, 12 should be here, 14 should be here, 15 should be here. So can I do this? Can I take the 6 here? But I have to right shift every one by one. How do you do it? You take 6, you take 15. And you say, okay, swap yourself. What happens is 6 goes here, 15 goes here, swap. Next you take 6, 14. 14 comes here, and 6 goes here. Next you take 6, 12. 12 comes here, 6 goes here. Next you take 6 and 9. 6 goes here, 9 comes here. So if I have to do it, it's like 6, 15, not in the correct order. So let's swap it. 15 comes here, and 6 goes here. 14, 6, no. 6 comes here, 14 goes. 6, 12, no. 12 comes here, 6 goes. 6, 9, no. 9 comes here, 6 goes. Perfect. It's like 6, 9, 12, 14, 15. So if I have to write it by raising, it's like 6, 9, 12, 14, 15. Perfect. I just went down to the left till it would have been swap, swap, swap. Right? Next, 8. In this particular array, where does 8 will go? Where will it go? In this particular array, where will it go? Ask yourself. The answer to that is 8 will go here. So if 8 has to go here, 9 has to go here, 12 has to go here, 14 has to go here, 15 has to go here. So again, what do you do? 8, 15. So you say, okay, 8 goes here, 15. So left. Can 8, 14? Can 8 go till 14? Yes. 14 comes here, 8 goes here. Can it go more left? Yes, it can. 8 goes here, 12 goes here. Can it go more left? Yes. 9 goes here, 8 goes here. Is it in the correct order? Yes. How do you know it? Because when you compared 8 with 6, it was not compared. None and dusted. 6, 8, 9, 12, 14, 15. 6, 8, 9, 12, 14, 15. Remember this? 6, 8, 9, 12, 14, 15. Next, 13 is the next guy that you are comparing. Can I say 13? Ideally over here should have been here. So do it again. 13 goes here, 15 comes here. 13 goes here, 14 comes here. Can I do a 13, 12? No. Stop. Can I say suppose the last? The array is sorted. Why? Because you picked up every element and you did put it into its correct order. So how did it work? I picked up 1. First time I picked up the first guy. Next time I picked up the second. Next time the third. Next time the fourth. Next time the fifth. Next time the sixth. Next time the seventh. Pick up. Every time. I'm running from index 0 to n minus 1. That's for sure. That's something for sure. I'm running from 0 to n minus 1. And what am I doing? What am I doing? Every guy on the left. That's why you don't go till 0, because right before 0 you put the last comparison. That's why. And that's why j minus 1, the last comparison. If it is greater than a of j, if it is greater, it means, can you please write? So I'm not writing the swap, you know how to write. You say a of j minus 1 and a of j. That's what you say. Right? And that's when it ends. And you get it was at 5. So with this, I can tick mark insertion sort, and it is completed. 3 is already in its correct position, 4 is already in its correct position, 5 is already in its correct position, 6 is already in. So this putting them into the correct position never happens. Suddenly, only this runs. Not check. It's a big off. It's a big off. The best case for this is nothing but big O of n complexity, because there is no swaps that happen. Everyone is at its correct order. You just go to everyone. That is what the time is taken for in case of insertion sort. So with this, I can tick mark insertion sort, and it is completed. The time is 5:29. Yes, because I do take a lot of retakes while recording, because I want it to be perfect. Like a lot of times I teach 2 or 3 times. So please, yes, because I do take a lot of retakes. So with this, I can tick mark insertion sort, and it is completed. The time is 5:29. Yes, because I do take a lot of retakes while recording, because I want it to be perfect. Like a lot of times I teach 2 or 3 times. So please, please for this effort, if you understood everything, do consider hitting that like button, and to follow our ritual, please do comment understood if you understood everything. And if you have doubts, you can definitely put that into the comment section. I'll be replying to them. And if you're new to our channel, what are you waiting for? Hit that subscribe. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So this is another lecture from the Strivers A to Z course. In case you're for the first time here, this is India's most in-depth DS Algo course. Why do I say that? Because this course has 456 modules and we will be solving more than 400 plus problems in this particular DS Algo course. You can buy any of the paid courses on the market. You can check out all the free courses on YouTube. You will not find such a comprehensive course on. So what is merge sort? It is nothing but one of the other sorting algorithms. You must be thinking, but Striver, till now you have taught us bubble sort, insertion sort, selection sort. So why this another algorithm? If you remember all of these three algorithms, we're taking big O of n square in order to sort an array. This is where merge sort is better. Merge sort takes a much better time complexity. We will be discussing the time complexity at the end of this video, but as of now you need to understand that merge sort is a much more optimized sorting algorithm. Now, you know sorting algorithm is nothing but it will sort a given data structure. If it has numbers, it will sort it according to numbers. If it has characters, it will sort it according to characters. If it has strings, it will sort it according to these strings. So as of now we know that merge sort is a sorting algorithm. So what will be the flow of the lecture? The flow of the lecture will be, first I'll explain the algorithm completely, then I'll go to the pseudocode, and since this is a recursive algorithm, I will go to dry run the recursion so that it gets into your head. So after these three steps, you will be able to code this particular algorithm in any of the languages because I will be writing the pseudocode. Post this, I'll be taking one of the languages and I'll be writing the main code. Again, this is something which is not that important. I will be focusing more on the first three steps. So without waiting, let's get started with the first step. That is the explanation of the algorithm. So in order to explain the algorithm, I will take this particular example of an array which has a size of 9. You need to remember two words. In merge sort, please remember that the algorithm means divide and merge. Please remember this, divide and merge. So as you can see that this array consists of 9 elements. If I have to ask you a question, how do you divide 9 elements into two parts? You'll be like, okay, there are two ways in which I can do it. One is I'll say 4 numbers and 5 numbers. That's one of the ways. The other way you can say is 5 numbers and 4 numbers. So that's two ways in which you can divide 9. Why? Because 9 is a odd number, so that cannot be split into two equal parts. That's why either you have to go 4 by 5 or 5 by 4. Now you can follow any of the path. I'll follow the 5 by 4 path. So if I follow the 5 by 4 path, what happens is this algorithm divides the array hypothetically. Very important word. This algorithm divides the array hypothetically into two parts and says 3, 1, 2, 4, 1 and 5, 2, 6, 4. What do you mean by hypothetically? When I will write the pseudocode, I'll explain you. Okay. So as of now, this algorithm has divided the array into two parts. One which has 5 elements and the other which has 4 elements. I can say left part and the right part. Now what I will do is I'll always take the left part and I'll try to divide it again. So let's try to divide it again. If I try to divide it again, what happens is it has 5 numbers. Remember this, it has 5 numbers. So you can divide it like 2 by 3 or 3 by 2. Now since in the first step I divided 9 into 5 and 4, bigger, smaller, I'll follow the same pattern. So that I can easily write a repetitive code. Now what I'll do is I'll try to divide it something like 3, 1, 2 and 4, 1. Remember one thing, you can also divide it as smaller, greater. That is completely okay. How you divide it doesn't matter as long as you divide it, okay? But make sure you follow the same pattern. Like over here, if you see it was 5, 4, there is greater, smaller. So follow the same pattern of division in the future as well for odd numbers. Okay, so next, 3, 1, 2. Go ahead and divide it. I follow the same pattern and let's say 3, 1 and 2. So it's like 2/1. Again, I'll try to divide it. And this time, there's 2 numbers. It's even. So it gets divided into 2 equal parts. So I'll divide it something like 3 and 1. Now, tell me what. Can this be divided further? The answer to that is no, we cannot because it's a single number and you cannot divide a single number. So this is where you stop. You say, the moment I get a single number, I stop. And you perform the second half of the algorithm. That states, please merge them. So what do you mean by merge? It is 3. So I'll write 3. It's 1. So they're basically two hypothetical arrays consisting of 1 numbers. So if there are two hypothetical arrays of 1 numbers, I want to make it a single array. What will I do? I'll say, okay, let's merge it. And you try to merge it into a single array consisting of these 2 numbers, but in a sorted way. So if I have to say, okay, I have 3, I have 1. And if I have to fill the first position, I have to make it sorted. Whom will I take? Will I take 1? Will I take 3? The answer to that is, I will take 1. So I take 1. Next two is remaining 3. So I've merged it. I'll explain merge in detail as the array gets bigger. But as of now, what you can say is, okay, we come back. Whenever it's a single element in both sides, we come back, we take them and we merge. And on merging, this will become 1, 3. This will become 1, 3. Perfect. Now, this 3, 1, 2 was divided into this portion and was divided into this portion. Can I say the left portion got itself sorted and on the right portion has a single element? Can a single element be further divided? The answer to that is no. So your next step will be very simple. You will take 1, 3 and 2. So can I say these are two hypothetical arrays? One is 1, 3 on the left, one is 2 on the right, and you'll try to merge them into a single because there are two hypothetical arrays. And if you carefully observe, the left array in itself is sorted and the right array in itself is sorted. So now I will go across and hypothetically try to merge them. If I try to merge them, they will give me 3 elements in the sorted order. Now tell me one thing. Do you take 1 or do you take 2 in order to fill this first position? You'll be like, hey Striver, I will take 1. So you took 1 and you did not take 2. So the moment you've taken 1, the next you will say, do I take 3? Do I take 2? Like I'll take 2. So you took 2. Next you're just left with 1. So you'll take 3. Again, I'll explain this algorithm in depth. Do not worry. So we basically merge them. Again, merge them. So we get 1, 2, 3. The merging has completed. So can I say, initially when I went to the left, we had 1, 2, 3. And when we went to the right, we had 4, 1. So the left portion has divided and merged itself into a single sorted array. It has. It's time to go to the right. Let's go to the right. So the moment you look at the right, it has 4, 1. So we again try to divide it. So if we try to divide it, it will be 4 and 1. Can I say we can stop over here because they are single elements and they cannot be further divided? Yes, we cannot further divide them. So what we do is we stop. Now, if it is 4, if it is 1, and if you have to merge them into a single sorted array, first 1 will come, then 4 will come. So what will happen is they will try to merge them and you'll get 1, 4. So can I say that this one went, got it sorted, but this one went and got it sorted. So basically, now they both will come back because the left half is sorted and the right half is sorted. If both of them are completely sorted, what will happen? So can I say it went left and it got itself sorted. It went right, it got itself sorted. It's time to come back. So they will get merged. Very simple. Let's write it again. 1, 2, 3 and 1, 4. And they will try to merge themselves into how many elements? Definitely, yes, 5 elements. So let's kind of now try to get into the algorithm. Now you know this is the smallest element on the left half. If I say there are two hypothetical arrays, can I say on the left, the smallest element is definitely on the beginning because both the arrays are sorted. So we will take 1, we will take 1. We have 1 over here, we have 1 over here. I have to ask you, which one will occupy this? It can be any of the ones. If I take any of the ones, maybe I'll just move it. Now, if I have to ask you, out of 2, out of 1, which will occupy this? You know the answer. It's 1. So you now move the pointer. Next, if I ask you, out of 2, out of 4, which one will occupy this? You will be saying 2. So I'll move the pointer. Next, if I ask you, out of 3, out of 4, which one does occupy this particular guy? You'll be like 3. And this will move out. Next, if I ask, which one will occupy this? You'll be like 4. And this moves out. So apparently, you got this entire thing sorted. So can I say this will become 1, 1, 2, 3, 4? Done. So this half is sorted. So we started with 9 numbers. We split them into 5 on this side, 4 on this side. 5 guys have been sorted. By the algorithm divide, and merge. They got themselves sorted. Now it's about these 4 elements. Can I perform the same algorithm of divide and merge on these 4? I can. So what I'll do is I'll again start, because now it's the right half's turn to get sorted. So I'll not again divide the 4 elements. And if there are even elements, how do they get divided? Into equal number of elements. So it will become 5, 2 and 6, 4. 5, 2 will become 5, 2. So again, can I say they will be sorted back into 2, 5. And now this one will take place. So it'll be like 6, 4. Again, it will come back. I'll say 4, 6. Perfect. Now can I say this portion is sorted? This portion is sorted. So now they will come back. And how will they come back? Let's write it out. 2, 5, 4, 6. So both of them will get merged into how many elements? 4 elements. 2 or 4. Which one goes at the first? 2. 4 or 5? 4 or 5? 4. Sorry. Now 6 or 5? Yes. 5. Next 6. It's like 2, 4, 5, 6. Very simple. So this becomes 2, 4, 5, 6. We can go ahead and erase this as well. Got a bit clumsier, but I'm assuming you're getting the explanation. Now where are we? Can I say we went to the left? We got everything sorted. We went to the right. We got everything sorted. The left 5 elements are sorted. The right 4 elements are sorted. What is that we need to do? We need to merge them. We need to perform the last step, that is merge. So these 1, 1, 2, 3, 4. 1, 1, 2, 3, 4. And on the right we have 2, 4, 5, 6. We have 2, 4, 5, 6. They will get merged into 9 elements, and that will be my ultimate sorted array. How do we merge? Let's now understand the algorithm in depth. So what we do is we keep a couple of pointers. 1 here, 1 here. Okay. And then we create an array of size, let's say 9. 1, 2, 3, 4, 5, 6, 7. We created an array of size 9, or you can create an empty array and keep on piling it up. That's your choice. We will take care of that during the implementation. So we know this entire left array is sorted. We know the entire right array is sorted. So we have to combine them to get a sorted array. So out of 1 and out of 2, because both of them are smallest, I have taken the 2 smallest guys from left, from right. Which one will take this place? You say 1. So you take 1 and you place it. The moment you've taken someone, let's just move the pointer. Let's start moving the pointer. Alright? You take 1 or you take 2. Again you take 1 and you move the pointer. You take 2 or you take 2. You can take 2 and you can move the pointer. You'll take 3 or you'll take 2. You'll take 2 and you'll move the pointer. Now will you take 4? Will you take 3? You'll take 3 and you'll move the pointer. Now will you take 4 or will you take 4? You can take 4 and you can move the pointer. So we can say the left array has been exhausted. Please hear me properly. I can say the left array is completed. It doesn't have any more elements that can go over here. So what I will do is, without doing any further comparisons, I'll pick up everyone from the right and I'll just put it over here. I'll pick up everyone from the right and I'll put it over here, because there is no one left on the left. Got it? If something similar happened, that the right element got completed, then you would have taken this and you would have put it in. Doesn't matter. So it's very simple. If I have to define the merge algorithm, it's very simple. Take 2 pointers, compare, put. One gets completed, the other one gets put. We will implement this, do not worry. So we have done the sorting. So the last step what will happen, they come back, and this will be 1, 1, 2, 2, 3, 4. 1, 1, 2, 2, 3, 4, 5, 6. 4, 4, 5, 6. So can I say, after I have completed all the steps of divide and merge, if you carefully notice, the last step was merge in the entire algorithm. So once I perform both of them completely on all the parts of the array that I get will always be sorted. This was the algorithm. I hope you understood. Okay, so I hope you have understood the explanation. That's time to understand the pseudocode. The first thing that we have to observe is, what are we doing? We are dividing. We are dividing the array into 2 halves. But logically speaking, if you're going to break the array down into 2 new arrays, and then again this array into 2 new arrays, again this array into 2 new arrays, will it make sense? No. This is where, in the pseudocode, we will try to play around with index. Instead of breaking them down into 2 new arrays, we will try to play around with indexes. Okay? So in order to write the pseudocode, what I've done is taken a very small array of size 5. I know the array indexing starts from 0 and it will go to 4 if the size is 5. So what I will say is, see, this index will be referred as my low. This index will be referred as high. So what does low and high means? It's a starting point of a hypothetical array, and high is the ending point of a hypothetical array. So initially, we have an entire array that has to be sorted. So low is the starting point of that entire array, and high is the ending point of that hypothetical array. Got it? Okay, so let's try writing pseudocode for this merge sort algorithm. So I'll go ahead and write the function name as merge sort. And initially, I'll pass the array, and I will say, in this array, initially, please consider the entire array that you have to sort. So the hypothetical starting point of this array is low, and this is high, which means take the entire array. So I'll pass him low, and I'll pass him high. And initially when this is called, low will be passed as 0, high will be passed as 4. Very simple. Let's go on. And as of now, I'll not write any condition. I'll keep conditions apart. So how do I write this algorithm? Let's try to observe something. What are we doing? Repeatedly. Are we doing something repeatedly? Yeah. Divide. Kind of doing divide. And the last step, we're trying to come back. Does it give you an idea that you have to apply something like recursion? Like you have to go divide, and then you have to come back. It's kind of like recursion backtracking. If you've seen the lectures, you can try to relate it with recursion and backtracking. That's what we will be using. So what I will say is, okay, now what is the thing that I'll do? I'll try to take this array and try to break it down into 2 parts. That is what I'm doing. I'll try to take this array and I'll try to break it down into 2 parts, where I will take the first one to be 3 to 4. That's how I was doing the creator, like 3 numbers at the first, and then the 2 numbers at the back. So I'll say I'll divide it into 2 parts, the left and the right. That's what I'm doing. And then I'll ask, can you please sort this? Can you please sort this? Once both of them are sorted, I can actually again merge them. That's what the algorithm was. So I'll be like, okay, do I need to make a new array? No. This is where low and high comes in. I say, hey, listen, this is array indexing. So can I say this array is nothing but an array where the low is at 0, an array where the high is at 2? Can I say this? I can. So if I have to look properly, the low is at 0, the high is at 2. That's what I'm doing. So I'll go and say that, hey, listen, maybe find a middle index. So middle is going to be low plus high by 2. Very simple. So if you see over here, what will be this? 0 plus 4 by 2 will give you 2. So where is the first half of the array? It's from 0 till 2. And where's the second half? It's from 3 to 4. So can I say, hey, please go ahead and try to sort this array which starts from 0, which is absolutely low, and which goes on till 2, which is absolutely middle, because in the first time the middle is 2. And can I say, okay, this means I'm asking him to do for this one, right? But I have to also ask him to do for this one, because if he sorts this, if he doesn't sort this, how will I merge them? Because both of them have to be sorted in order to be merged. So what I will do is, I'll again say merge sort. When I say array, can I get the right half of the array sorted? I'll be like, okay, in this array, which portion are you telling me to sort? I'm saying from 3 to 4. What is 3? That's nothing but mid plus 1, because mid was 2 until high. So what I've done is, instead of making 2 new arrays, I told the indexes. I told, in this array, take from low to mid, which is take from 0 to 2, which is this. In this array, take from 3 to 4, which is this. Instead of dividing them into 2 arrays, I passed on the indexes and set them to 1. Set them to sort themselves. Now, assuming that these functions are getting sorted by themselves, once the portion from low to mid is sorted, once the portion from mid 1 to high is sorted, what is the next step? If you remember, the next step is merge. So probably I can say that, hey, please go ahead and merge the array. The first half of the array is very simple. It goes from low to mid, and the second half will be from mid plus 1 to high. So take these things, and can you please merge this particular array? That's what I'm saying. Very simple. Now, when do we stop? When do we stop is my question. We have to write that over here, because if you know, if this is nothing but a recursion. Merge sort calling itself. It's a recursion. In order to stop recursion, you write something as base case. I hope you know that. In order to stop recursion, you write something as base case. So to write that base case. Let's analyze what is the base case. Let's go back to this example. What is the base case? Can I say when your array has one element? So if I have to index it, can I say this is index 0, this is index 1, this is index 3, 2, 3, 4, 5, 6, 7, 8. Can I say these are the last indexes? And if I have to ask, what array is this? You'll be like, this array is something like from index 1 to index 1, where index 1 is the low, index 1 is the high. Can I say this is the array that represents this? Yes, because we are not creating a new array. I am saying this array is from index 1 to index 1, which is this. Right? So can I say the moment we have the low, the left point, we have the high, the right point to be same. That's when we do not go and divide. We do not divide. We just go back. So that's what the base case will be. We write, hey, if at any moment the low tends to be equal to high, or exceeds high for that reason, or maybe it's somehow like it will never, but still, just for safety reasons, if it exceeds high, please do not, because there's no need to do any of the further algorithms. It's a single element array, and it will always be sorted. Please go back. So this is how the pseudocode will look like. Might seem a bit confusing, but now when I'll write and by taking an example, it'll straight away get to your head. Okay, so we can say that the pseudocode has been completed, but in order to understand this algorithm with clarity, we have to do a dry run of this recursive algorithm. Then only it will get clarified. So let's try to do a dry run by taking this particular example. So remember one thing: whenever this algorithm is called, it is called with the complete array. So the entire array has always been passed with this algorithm, and the initial low and high will be 0 and 4, because that's what for this particular example it will be. Because initially I will pass on this entire array and ask merge sort to sort it. So what will happen? Will this first base case operate? Because no, low is still smaller than high, so it doesn't. Mid comes out. What will be the value of mid? Can I say the value of mid will be 2? So what happens is, it goes ahead and calls the merge sort. So let's copy paste the same algorithm. Let's do it. So I've copy pasted. So what we can say is, this particular recursion call will call this particular function again, but this time it will pass the low as 0 and pass the high as 2. So apparently what happens is, it calls for this guy. Remember how recursion works is, first this will get operated, comes back, then this line gets operated. That's how recursion works. So that's why first the left portion will get operated. So the recursion call for 0 to goes. Now what happens? Does this line operate? No, this line doesn't operate. What happens? Tries to find the mid, and this time the mid comes out to be 1, because 0 plus 2 is 2, and 2 by 2 is 1. So 1 comes out. So this time again this merge sort gets called. But if the merge sort gets called, what will happen? It gets called for what? From 0 to 1. So it's like 3 to 2 is what it is getting called. And then it will be called for the only number 4, which is just 2. So we will go ahead and maybe again call this recursion. Let's go ahead and call the recursion again. So the recursion is again called. What happens this time? The merge sort is called with 0, 1, which means this particular example, right? So this time the low is 0, the high is 1. So what happens? The mid is 0 plus 1 by 2, which is nothing but 0. So again, the merge sort is called. So let's again copy paste this same algorithm. The merge sort this time is called for 0, 0. If I go into the diagram, it's something like for 3 and something like for just 1. So this time it's called for 3. So what happens is, it's called for 0 and 0. So apparently this particular base case gets executed and it returns. So I can say it's done. So if I have to go back into the chart, this goes back. Similarly, another merge sort will be called, let's try to write this as well. And this time it will be called for from mid plus 1 to high. So mid was 0, so it will be like 1, 1, because high was 1. Mid was 0, so mid plus 1 is 1, high is 1, so high is 1. It's called for 1, 1. Again the low, the base case operates and it calls back. Apparently both of these recursive functions are completed. Once both of these recursion functions are completed, can I say this? That I'm going back from here. And now we have this as sorted, It's two sorted arrays. What will happen? Let's go back here. This merge happens. So it takes a 3, it takes a 2, and it tries to merge it. Now we will like the merge algorithm afterwards, but let's understand. Just imagine merging 2 arrays. That's it. That's a very simple algorithm. Just understand this. So 2, 3 happens. So what would have happened? 2, 3, right? So this would have become 2, 3. Perfect. Let's go back to the recursion. So can I say, now we can go back from here to here, and we can say the 0, 1 is sorted. So this time this recursion will again be called. Let's try to write it. So what will be this recursion? If 0, 1 is done, If 0, 1 is done, what's the next? Mid plus 1, that's 2, I is 2. So we'll call it for 2, 2. And if we call it for 2, 2, what will happen? Yes, they're the same numbers. So it will return. And if it returns, this time what will happen? It called for 2, 2. This guy has done the recursion, and this guy has done the recursion. So apparently, again the merge happens. This time the merge happens from 0 to 1 till the 2. The merge this time happens for 2, 3 and maybe 4 or whatever it is. Yes, and this will become 2, 3, 4. Hope you're getting the gist. So can I say, after this, I'll again go back And when I go back, now I'll try to just come back. Yes. When I go back, can I see this? That 0, 2 would have been sorted. And if 0, 2 is sorted, I'm done with this. I'll go to the right part, which is having this. And similarly, this is done. So this will call it, right? And I will call it, let's copy paste and show it. If 0, 2 has been done, so can I say next is mid plus 1? So this is nothing but 3, high is 4. This time it goes and calls for 3, 4. Again, the same thing will happen. The mid will be 3 plus 4, 7 by 2, 3. So it will be called for 3, 3, and then it'll come back. This will be called for 4, 4. It will be come back, and then this will merge both of these two elements. It's like it will be called for 1, it will be called for 3, then they will be merged as 1, 3. And once this is done, what do we have? We have 0, 2 sorted. We have 3, 4 sorted. So the last merge takes place between this 0, 2, that is 2, 3, 4, and 1, 3. So apparently they are merged together. When merged, you'll get 1, 2, 3, 3, 4. That is what happens at the last step. I hope that does make sense. So I hope the dry run is clear in terms of the pseudocode. It was very simple. First, the entire array goes to the left, goes to the left, goes to the left, goes to the left, and then merges. It always performs this recursion first, this recursion first, this recursion first. Once this is completed, then this. Once both are completed, then the merge happens. You need to understand. So this is how the flow works. In order to understand this in much more depth, what I'll recommend you is take a pen and paper, write this code, try doing it all over again. Got it? So what have we completed? We have completed the dry run, the pseudocode as well. But before going into the code, we still are left with the merge pseudocode. If we are able to write the merge pseudocode, I think we will be done. So let's take a bigger example in order to understand the merge pseudocode. Can I say the indexing is like 0, 1, 2, 3, 4, 5, 6, 7, 8, and this is like 0, 1, 2, 3, 4, and this is like 5, 6, 7, and 8. And if the merge will happen, I will call it like merge these two arrays, because if you know this array when goes into depth, it will be sorted. It will be sorted like 1, 1, 2, 3, 4, and this also will go into the depth, and it will be sorted like 2, 4, 5, 6. This is something which all of us know for sure, that both of them will be sorted. And both of the array will be something like 1, 1, 2, 3, 4, and this will be like 2, 4, 5, 6. This is something we know. And this will be indexed from 0 to 4, this will be from 5 to 8. That's something we know. We just have to write an algorithm to do it. So we're writing the algorithm, okay? So we're saying merge. I'll give you the array, and I'm stating you that the first half is from low to mid, and then you can go from mid plus 1 to high. So I'm giving you all the 3 parameters required. What I'll do is, maybe I'll just keep an empty data structure. It can be a vector, it can be a list. As of now, just imagine this is an empty data structure where we can add elements. Okay. Now, can I say that the left array will be from low to mid? And can I say the right array will be from mid plus 1 to high? I can. So I will keep a couple of pointers. So I'll say, okay, left pointer is at the low. So that means left comes over here. And I'll say right pointer is nothing but at mid plus 1. So what happens? I'll say right is here. Now what will I do? I will try to compare these two and try to fill in this bigger array, the bigger array. I'll try to compare these two and try to fill in the bigger array. So what I will do is, I will now try to iterate till what? Till we have elements on the left, or till we have elements on the right. Can I say, that means I will say while left is smaller than equal to mid, which means I still have element. I'll say and right is lesser than equal to high, which means I still have elements on the right. Very simple. Now what I'll do is, okay, this is what I'll do. Till I have elements on the left, till I have elements on the left, on the right. So I'll not try to compare. I will say, hey, listen, if array of left is smaller than equal to array of right, so what happens? This and this gets compared. And if 1 is smaller than 2, I'll take 1 and I'll add it to our resultant guy. So I'll say, okay, maybe we can name this as something else. Let's go and name this as maybe, let's say, temporary. That's a better name. I'll say temporary. Can you please add yourself the smaller guy, array of left? And once you've done this, can you move ahead the pointer? Which means the left pointer goes to the next. Again, so basically what will happen is the temporary will have 1 with itself.
जी, कैसे हैं आप सभी। ये वीडियो सबसे एंड में मैं रिकॉर्ड कर रहा हूँ ताकि इस सीरीज़ का मैं आपको पोटेंशियल और क्या इंटेंशन है इस सीरीज़ के पीछे ये आपको बता देता हूँ। ये सीरीज़ है कम्प्लीटली रिकर्जन के ऊपर और इसका गोल ये नहीं है कि मैं आपको रिकर्जन एंड टू एंड सिखा दूंगा या इसके सारे क्वेश्चन हम कवर कर लिए, नहीं। ये सीरीज़ बड़ी ही लाइट वेट बनाना चाहता था। अगर आपके मान लीजिए 15 दिन बाद कोई प्लेसमेंट्स हैं, कॉलेज में
हेलो, वेलकम अगेन। दिस इज अंसारी एंड यू आर वाचिंग शेरियंस कोडिंग स्कूल। ये है डीएसए सीरीज का एक और धुआंधार लेक्चर जहां पर हम देख रहे होंगे रिकर्जन लेवल 1, जहां हम देखेंगे कि यार व्हाई वी नीड रिकर्जन, हाउ रिकर्जन वर्क्स, व्हाट इज रिकर्जन और उसके कुछ एप्लीकेशंस, आई मीन क्वेश्चंस। भाई क्वेश्चन के बिना तो लेक्चर अधूरा है ना। और एक और चीज कि यार हम स्टैक मेमोरी के बारे में भी समझेंगे, क्योंकि अगर हमें स्टैक मेमोरी का फंडा समझ में आ गया कि हाउ स्टैक मेमोरी वर्क्स और कॉल स्टैक क्या होता है, तो रिकर्जन पढ़ने में बहुत ईजी और आसानी होगी। एक सवाल और आता है कि भैया आपने टाइटल लिख के रखा है रिकर्जन लेवल 1, तो इसका मतलब कि क्या इसके एडवांस लेवल भी आएंगे? बिल्कुल हाँ, विद सम एडवांस क्वेश्चंस। तो गारंटी देता हूं कि लेक्चर पूरा समझ में आएगा। इससे पहले आपने कभी भी रिकर्जन पढ़ा था, समझ में नहीं आता था, पर इस लेक्चर में समझ में आएगा, बस बरकरार रहना। तो चलो आओ अपन स्टैक मेमोरी पहले समझते हैं। ओके, सो बेसिकली जो हमारे स्टैक मेमोरी में स्टैक डेटा स्ट्रक्चर का प्रिंसिपल पे काम करती है। अब स्टैक डेटा स्ट्रक्चर का प्रिंसिपल क्या बोलता है? सर मैं जो हूं, मैं क्या हूं? लीफो हूं। लीफो मतलब क्या होता है? लास्ट एंड फर्स्ट आउट। मतलब कि गिवन स्ट्रक्चर में जो कुछ भी एलिमेंट लास्ट टाइम इंसर्ट होती है वो सबसे पहले रिमूव या फिर पॉप होती है, या फिर आप कह सकते हो उस स्ट्रक्चर से बाहर निकलती है। लेट्स से मेरे पास कुछ बंच ऑफ बुक्स हैं जिसमें आप दिख रहा होगा 1 2 3, मतलब कि मेरे पास 3 बुक्स हैं और मैंने क्या बोला कि भैया इसमें क्या कर दो, एक बुक कर दो, और यही लास्ट इंसर्टेड बुक है। और जब भी मैं इन फ्यूचर कभी भी इसमें से एक बुक पिक करूंगा तो कहां से पिक करूंगा? टॉप से पिक करूंगा। कहां से? टॉप से। और भी आपने कई एग्जांपल देखेंगे, जैसे कि हमारे पास शादी वगैरह में कहीं जाते हैं अपन खाना खाने के लिए, और कहीं ले जाएंगे, खाना खाने के लिए जाएंगे, तो वहां पर आपने देखा होगा स्टैक ऑफ प्लेट्स रखी रहती है। तो जो भी लास्ट इंसर्टेड प्लेट होती है वो सबसे पहले हम उसको क्या करते हैं? पिक करते हैं। सिंपल सी बात है। आपने और एग्जांपल लिखेंगे, जैसे कि हमारे पास क्या होता है? स्टैक ऑफ चेयर्स होती है, जो सबसे लास्ट इंसर्टेड चेयर रहती है, हम उसी को क्या करते हैं? पॉप या फिर रिमूव करते हैं। और मैं आपको एक रियल लाइफ एग्जांपल बताऊं, हमारे कंप्यूटर के टर्म्स में जब भी आप अंडू रीडू करते हो, अंडू रीडू, तो जो कुछ भी लास्ट टाइम एक्शन हुआ होता है वो सबसे पहले क्या होता है? अंडू होता है। वो भी वहां पर भी बिहाइंड द सीन्स क्या लग रहा है? एक स्टैक डेटा स्ट्रक्चर लग रहा है। चलो तो वापस आते हैं। अच्छा बाय द वे, अगर आपको नहीं पता होगा तो स्टैक डेटा स्ट्रक्चर को हम बिल्कुल डीप में पढ़ेंगे, डेप्थ में पढ़ेंगे और उसके कई अच्छे क्वेश्चंस करेंगे कुछ लेक्चर्स के बाद। अभी अपन आते हैं कहां पर? स्टैक पे। अब होता क्या है यहाँ पर? होता क्या है, जब भी हमारे स्टैक मेमोरी में कोई भी एलिमेंट कुछ भी इंसर्ट करते हैं तो हम उसको क्या बोलते हैं? पुश बोलते हैं। और जब भी हम कुछ भी एलिमेंट को बाहर निकालते हैं उसको क्या बोलते हैं? पॉप। सो इन शॉर्ट, पुश एंड पॉप आर व्हाट? ऑपरेशन। क्या ऑपरेशन से फंक्शंस होते हैं जो कि क्या करते हैं? कुछ एक्शन परफॉर्म करवाते हैं। और इनके जो टॉप का एलिमेंट होता है हम उसको क्या बोलते हैं? पीक एलिमेंट बोलते हैं। क्या बोलते हैं भैया? पीक। हमारे स्टैक मेमोरी को एक और नाम दिया गया है, वो क्या है? कॉल स्टैक। क्या है? कॉल स्टैक। सवाल आता है कि भैया आप कॉल स्टैक नहीं यार, क्या लिख रहा हूं? एक मिनट, कॉल स्टैक। हमारे स्टैक मेमोरी को भैया आपने कॉल स्टैक क्यों बोला? समझाता हूं, समझो आप। हमारे स्टैक मेमोरी में जो कुछ भी एलिमेंट है वो क्या होती है? फंक्शन कॉल होती है। क्या होती है भैया? फंक्शन कॉल। मैं आपको एग्जांपल के थ्रू समझाता हूं, पहले मैं कोड लिखूंगा फिर वापस अपन क्या समझेंगे? स्ट्रक्चर समझेंगे। लेट्स से मैं कहां पहुंचा? हमारे वीएस कोड पे। और सर मुझे वीएस कोड मिल जाएगा? बिल्कुल मिल जाएगा, क्यों नहीं मिलेगा? जैसे कि मैंने क्या बोला कि मेरे पास एक फंक्शन है, फंक्शन का नाम क्या है यहाँ पर? फंक्शन का नाम मैंने यहाँ पर क्या ले लिया? ग्रीट ले लेता हूं। लेट्स से मैंने यहाँ पर क्या बोल दिया? ग्रीट। और ये मैंने एक फंक्शन बनाया और मैंने यहाँ पर क्या बोला कि आप यहाँ पर प्रिंट करवा दो गुड मॉर्निंग पाइनएप्पल। गुड मॉर्निंग पाइन एप्पल। ठीक है, ऐसा कुछ है ना, ऐसा कुछ। लेट्स से एक और मैंने यहाँ पर एक फंक्शन लिया जिसका नाम है फंक्शन